This episode of Real Engineering is brought to you by the Curiosity Stream and Nebula Bundle Deal. Watch the latest episode of our new series, The Battle of Britain, on Nebula for just $14.79 a year. In 1969, a pioneering vision of the future made its debut to the public.
In a few years' time, the sight of Concordes on international airfields all over the world will be commonplace if all goes well. Then there'll be 130 passengers on board. Flying times will have been cut by half. London to New York from 7 hours 40 minutes to 3 hours 25 minutes.
The juxtaposition between this dated footage and the futuristic plane is strange. It's hard to believe passengers 40 years ago, in a time when colour TV was a luxury, were flying across the Atlantic at the speed of sound. The Concorde was well ahead of its time, an anomaly in the history of commercial travel, a byproduct of misguided government funding, a joint venture between Britain's BAC and France's Aerospatiale, and its development funded entirely by the British and French governments to the tune of $2.8 billion. The Concorde's legacy is marred by its commercial failure, but this engineering marvel was a triumph of ingenuity. Nothing remotely close to it had flown before, and nothing like it has flown since, turning what had been a military-only technology into a luxury flying experience required innovative thinking. This is the insane engineering of the Concorde. The engineers of the Concorde had several unique challenges. Developing a supersonic plane is difficult enough with military design requirements, but developing a supersonic plane that would satisfy the wealthy customers it intended to serve is an entirely different ballgame. Aerial refueling makes fuel efficiency a secondary concern for the military. The comfort of the plane's passengers is an afterthought at best, and the price tag attached to these often limited-run specialty planes is beyond the budget of a commercial airline. Those needs are reflected in the Concorde's unique design. A sleek exterior hiding powerful engines. Engines developed from the iconic British warplane, the Avro Vulcan. Fuel efficiency and supersonic flight are two opposing ideas, but these engines, the Rolls-Royce Olympus 593, when flying at Mach 2, were the most efficient engines ever created. These engines, when introduced for the Avro Vulcan, were capable of generating just 49 kilonewtons of thrust, but over the course of their adaptation for use in the Concorde, increased in thrust by over triple to a whopping 169 kilonewtons. 20% of this thrust increase was provided by newly fitted afterburners, a technology typically reserved for military planes. Afterburners work by injecting fuel directly into the superheated and high-pressure exhaust of the turbine section. Despite this air's journey taking it through the combustion chamber, only half of the oxygen in the air is consumed, leaving untapped energy in the exhaust of these engines. To capture this energy, fuel can be injected directly into the exhaust of the turbines and ignited, basically acting like a rocket stage of the engine, causing further expansion and acceleration of the exhaust through the exhaust nozzle. However, this system is useless without a controllable nozzle. Typical airliner engines have a fixed nozzle, because these aircraft are expected to be efficient at a relatively low range of subsonic speeds. But the Concorde, with its massive range of speeds, needs not one, but two controllable nozzles to adequately control the engine's power. The primary nozzle connects directly to the jet pipe's exit and consists of petal-like structures that can close or open to vary the diameter and therefore the area of the jet's exit. When the afterburner, or reheat as the British engineers called it, was ignited, it caused a massive increase in pressure at the engine's exhaust. This increase in pressure could cause choked flow in the engine, where high pressure zones ahead of lower pressure zones will prevent air from flowing through the engine correctly. To prevent that, the primary nozzle opens wider when the afterburner is active to decrease pressure and ensure the mass flow rate through the engine is unchanged. However, at times, we do want to affect the flow upstream of the nozzle. The Olympus 593 was one of the world's first, predated only by the Pratt & Whitney J57 engine by just a couple of months. Two-spool means the engine contained two compressor sections driven by two turbine sections, each acting on their own concentric drive shafts, allowing the two sections to operate at different rotational speeds. When the primary nozzle was actuated, the varying nozzle pressure caused the low-pressure spool to either spin faster or slower, thus providing control of the engine to ensure it can perform at its optimum speed across its wide speed range. The secondary nozzle function is just as complex. The eyelet doors look like some kind of steampunk blast shield, and for good reason. The force these secondary nozzles had to endure influenced their appearance, withstanding huge forces at both supersonic and subsonic speeds, and they could even close completely on landing to function as reverse thrusters. By actuating these nozzles, the plane could carefully manipulate the exhaust velocity and thus maximize thrust because together the pair acted as a controllable converging-diverging nozzle. Converging-diverging nozzles are typically used in rockets to accelerate the combustion products to their optimum speed and pressure. The opposite shapes are needed because air acts completely differently at subsonic and supersonic speeds. For example, when subsonic air travels through a converging duct, it speeds up as the cross-sectional area decreases until some critical area, which is referred to as the throat. This is where Mach 1 would be reached. At this point, no further acceleration of air can occur as the flow is choked. Now, as you would expect, if that same subsonic airflow went through a diverging duct, the air slows down as the duct area increases. This is Bernoulli's principle at play. The bizarre thing is, the exact opposite occurs when air travels at supersonic speeds. A converging duct will result in a decrease in velocity, and a diverging duct will result in an acceleration. So, in order to maximize the acceleration of our exhaust gases, we want to pass our subsonic air from the engine first through a converging nozzle, the primary nozzle, until it reaches Mach 1 at the throat. Then we want it to pass through a diverging duct, the secondary nozzle, at supersonic speeds so it can continue to accelerate. These paired nozzles allowed the Concorde to carefully optimize the nozzle profile for different flight conditions, a marvelous piece of engineering. The same principles were used for the inlet. No engine can operate with supersonic flow. The shockwaves that would form inside the engine would cause all kinds of chaos. So, the Olympus 593 needed some way to decelerate the supersonic air entering its unique square inlets. These squared inlets were designed to simplify the complicated task of creating nice laminar subsonic flow for the engine's compressors. Inside were a series of ramps and doors that could open and close depending on the flight regime the intake was encountering. At takeoff, the engines required all the air they could get to accelerate the plane enough to get those cumbersome delta wings to generate enough lift to take off. To funnel as much air as possible into the engine, the two variable ramps were retracted into their closed position. A spill door in front of the engine intake was held open to allow additional airflow into the engine, while two bypass doors which controlled the air around the cooling passage around the engine were also closed. The afterburners were also active during takeoff, but soon after, the Concorde was required to enter a noise abatement stage of flight, where the afterburners were turned off and power was reduced as the plane climbed. At this point, the bypass doors open to allow for cooling air to travel along the outside of the engine. As speed increases, the primary and secondary nozzles adapt, gradually beginning to form the ideal converging-diverging nozzle for supersonic cruise. Parallel to these changes in the nozzles, the inlet ramps actuate to create a converging inlet that slows down and compresses the supersonic air entering the engine. The fuel consumption of supersonic flight is massive, but that is primarily driven by aerodynamic drag, not thermal efficiency. This supersonic air being rammed and compressed into the engines help the engine immensely in achieving its high thermal efficiency. Thermal efficiency in jet engines is largely determined by the pressure ratio achieved by the engine. That is the ratio of pressure between the inlet of the engine and the outlet of the compressor, which, in the case of the Concorde, flying a cruise, is 80:1, an incredibly high pressure ratio. The highly efficient GE and X engines of the Boeing 787 only manage 58:1. The Olympus 593's two spools each contained 7 compressor stages, each driven by a single stage turbine. The low pressure and high pressure compressors together provided a pressure ratio of 14:1, a moderately high pressure ratio that would provide moderate efficiency at subsonic speeds. However, the pressure ratio multiplied to 80:1 at cruise as the supersonic air rammed into the unique square inlet engines. This elevated pressure ratio resulted in extreme temperatures inside the engine that necessitated the use of high-temperature alloys that are typically reserved for the turbine blades. Titanium blades were used for the early compressor stages, and high-temperature nickel alloys were used in the even hotter later stages. Cooling the driveshaft bearings became another engineering challenge. Increasing the mass flow rate of cooling oil was not enough to keep the bearings within a safe operating temperature. Looking at the differences between the original Olympus engines used in the Avro Vulcan and the Concorde hints towards some changes the engineers were forced to make. A center bearing located immediately after the high-pressure compressor here no longer exists in the Olympus 593, and the driveshaft preceding it takes a bottle-like shape, increasing in diameter in the new gap between bearings. This center bearing had to be removed because the temperatures were too high in this location directly after the high-pressure compressor. But without the support of the bearing, the driveshaft became too flexible. To accommodate this change, the driveshaft needed to increase in diameter to increase stiffness. The Concorde is full of strange little design details like this, solutions to unique engineering problems caused by the immense cruising speed. In order to decrease fuel consumption as much as possible, the front area of the plane needed to be minimized. Delta wings allow wing spans to be decreased dramatically and reduce the drag created in supersonic flight. However, it creates some issues for low-speed flight, where they struggle to generate enough lift, making takeoffs and landings difficult. This is where the ogival delta wings of the Concorde come into play. This is a form of compound delta wing where there are 2 sections to the wing, with the forward section having a higher sweep angle than the rear section, connected with an OG curve, going from concave to convex curves smoothly. This shape allowed the Concorde to generate additional lift at low speeds through the use of vortex lift. When flying at high angles of attack, separated airflow would roll over the wings to form 2 stable cone-shaped vortices, where airspeeds were high and air pressure was low, effectively creating lift. However, those high angles of attack needed for low speeds created some serious visibility problems for the pilots, whose cockpit would have had a lovely view of the sky if not for the iconic droop snoot. The droop snoot is a one-of-a-kind solution, a mechanized nose that could drop by 12.5 degrees to provide the pilots a clear view of the runway during these high angle of attack maneuvers. The mechanism had 4 positions, controlled by the pilot with this lever. The top position was the fully retracted position used in supersonic flight. The second position lowered a specialized heat shield visor used to protect the cabin windows from the heat of supersonic flight. When placed in this position, the visor hydraulic actuator would retract, causing the visor to retract into the nose fairing. The next position was the 5-degree down position used for takeoffs and taxis, extending this hydraulic actuator, and the final setting pushes the nose down further into the 12.5-degree setting needed for landings. The plane also had an extendable tail landing gear, which on most takeoffs and landings was not needed, but was present to protect the plane's engines, which would be the first point of contact for what would normally be a tail strike for other airliners. Tail strikes aren't all that uncommon, usually happening on landings in difficult conditions. Some planes, like the 777, also have extendable protection measures in the form of tail skids, as a strike can, at best, force a plane into maintenance, costing the airline company money, or, at worst, cause serious damage to the pressure bulkhead and put the lives of the passengers aboard at risk. In fact, a tail strike is responsible for the crash that claimed the most lives out of any single aviation crash in history. In 1985, a Japan Airlines 747 flight crashed in the mountains of Japan, 7 years after a tail strike had occurred, which had not been correctly repaired. With the high angles of attack demanded by the Concorde for landings, this protection was vital to keep the plane safe. The visor was needed during supersonic flight because the nose of the plane experienced temperatures of around 130 degrees Celsius, while cruising at an altitude of 60,000 feet, where ambient temperatures are usually around minus 56 degrees Celsius. The Concorde went through several design iterations with this forward-facing protection. The earliest prototypes simply removed the lower forward-facing windows completely. But it turned out that pilots like having a view of where they are going, so this wasn't an option for the full production model. However, a version of the droop snoot with a fully metal heat shield was originally considered for the Concorde, which would have eliminated forward visibility during cruise, which was considered non-essential. But thankfully, these heat-resistant glass visors were used in the final version. Working with such high temperature variations between takeoff and landing causes some serious structural issues, especially with the frequency of flights needed to make a commercial plane financially viable. The thermal expansion caused by these temperatures made the plane grow by 20 centimeters on each and every flight. The fatigue this thermal stress could cause would eventually result in catastrophic failure if not properly accounted for. The first issue was finding a material capable of dealing with this heat. Titanium, which was used for the SR-71, could have been used, but due to its cost and weight was ruled out early. Traditional aluminium would not be capable of withstanding these conditions, but a special aluminium alloy, Hindaminium RR58, developed in Britain during World War II for the newly invented gas turbine engines, could. The alloy consists of copper, magnesium, silicon, iron, nickel, and titanium, with the remaining percent being made up of aluminium. Although this material had been developed decades prior to the Concorde, it had never been used in this application. With lower average temperatures than its traditional use inside gas turbine engines, but much longer life requirements, the parts would also be manufactured using different techniques, like the cold-rolled sheets needed for the fuselage. This one process alone affected critical material properties that improved heat resistance. Forged parts tend to have larger crystal grain structures than rolled components, which helps forged components resist the internal crystal structure from creeping when under stress and heat. To adapt this material for the cold-rolled skin of the Concorde, the engineers at Rolls-Royce had to develop new manufacturing methods to maximize the grain size of these cold-rolled components. Manufacturing knowledge that has no doubt been used by Rolls-Royce for modern-day applications. Now that a suitable material had been developed, shaping it in a way that allowed expansion was crucial. Most of this expansion was imperceptible to the crew and passengers of the Concorde, Interior panels could slide past each other to hide the expansion to the passengers, and crucially prevented stress forming as a result of uneven expansion between the hot exterior and cool interior. Wiring around the plane was given slack to prevent the wiring from snapping as the plane expanded, and many components around the plane were corrugated, meaning parts were given a curved shape. This allowed these parts to stretch and flatten the curves like a spring. However, one expansion gap was quite obvious to the crew of the Concorde. As the flight approached its cruise speed, a gap between the flight engineer's console and the cockpit bulkhead began to form, a gap large enough to slide your hand inside of. Or, as became tradition for retiring Concordes, the flight engineer's cap would be placed inside the gap as it closed, leaving it permanently wedged. Like the SR-71, this continual expansion and contraction cycle caused some serious issues with fuel tank sealants. In order to deal with the expansion cycles, a sealant needs to be flexible. Even mundane plastic sealants on household windows need this quality to prevent small movements from allowing drafts getting through. The issue is that high temperatures tend to harden sealants over time, and then, as the expansion cycles continue, the sealants begin to crack and allow fuel to spill out. While the temperatures the Concorde experienced were vastly lower than the SR-71, it was still a maintenance issue. The Concorde used a high-temperature sealant called Viton, but even this sealant hardened and cracked over time, and so, approximately every 1,100 flying hours, roughly once a year, the Concorde was forced into maintenance, which could take 3 weeks to complete. Maintaining the Viton seals was one of the many procedures needed. Fuel tanks would be emptied and then vented for 24 hours to allow technicians to climb inside and manually inspect and replace sealant. This was a massive job and often required the technicians to work with just touch, as access to tanks 5A and 7A on the outermost part of the wing was impossible. The Concorde had 13 separate fuel tanks in total, taking full advantage of the large amount of interior volume the Delta wings provided. Without these fuel tanks, capable of holding 119,000 litres of fuel, the Concorde could not have made it across the Atlantic and would have been completely useless. To put that volume into perspective, a typical Boeing 787, the world record holder for longest commercial flight, can hold just 34,000 litres of fuel. These fuel tanks played a vital role in control of the plane too. As speed increases, the centre of pressure of a wing, the point through which all lifting force acts, tends to move backwards. This is usually not a significant issue for slower commercial airliners, but the Concorde's centre of pressure moved back by as much as 1.8 metres, more than enough to cause significant control issues that would push the plane into a nosedive if not accounted for. Usually, such a shift would be counteracted by the elevator, which could stabilise the aircraft in pitch from changes in the centre of pressure. But Concorde did not have a horizontal tail, and adding elevons on the wing big enough to counteract this change would have resulted in high levels of trim drag at such high speeds. So, Concorde engineers instead used the huge tanks they had at their disposal to deal with this issue. As the plane approached Mach 2, fuel would begin to be pumped out of the forward trim tanks and into the rear trim tanks and collector tanks in the wing, moving up to 20 tons of fuel rearwards and shifting the centre of gravity backwards to match the shift in centre of pressure, keeping the plane balanced without adding any additional drag with control surfaces, an elegant solution using the tools at hand. The Concorde is an icon in the history of aviation. I can't help but feel an odd sense of nostalgia for a plane I never got to fly in. Hundreds of thousands of passengers can see one of the last remaining Concordes while arriving and departing from Heathrow. Nicknamed Alpha Bravo, this Concorde made its last flight a month after the tragic loss of Air France 4590. It was undergoing major interior upgrades when the decision to retire all Concordes was made, stranding the plane there indefinitely. Alpha Bravo has been in limbo ever since. never getting to undergo the planned upgrades to prevent another disaster like Air France 4590 from ever happening again. An unintentional monument to Britain's storied history in aviation. Accidental monuments like this are scattered all across Britain. Gigantic, no longer functional radar towers can be found all over Britain. These towers were among the first radar systems ever constructed and played a vital role in the defence of Britain during the Battle of Britain, a system that the Germans vastly underestimated, thanks to not just the technology, but the logistical and strategic systems that supported them. This is the story of our latest episode of our Battle of Britain series that delves deep into how Britain's radar systems worked and how those systems were integrated into an effective intelligence system. You can get access to the entire Battle of Britain series and our Logistics of D-Day series by signing up to the Curiosity Stream and Nebula bundle deal for a little over $1 a month. With this yearly subscription to Curiosity Stream, you can enjoy the mountain of award-winning documentaries on Curiosity Stream and support independent content creators like me over on Nebula. This is the best way to support this channel. Nebula gives us a place to experiment in safety, without any worries of alienating our current audience on YouTube or being demonetized for covering sensitive topics like war or tragic disasters. Your support there has helped this channel evolve and grow, and we are able to give you exclusive content like this as our thanks. You can sign up to this amazing deal by clicking on this button on screen right now, or if you're looking for something else to watch right now, you could watch our latest video on the incredible engineering of the Parker Solar Probe, or you could watch Real Science's latest video on the strange, new, man-made life forms, xenobots.